So, structured questions from the topic general wave properties. And some of the questions certainly would include water waves as well. Here we have the first one, figure 4.1 and 4.2 are diagrams of the ripple tank used to show two properties of waves. A. Figure 4.1 shows wave fronts approaching a barrier in the water. Complete figure 4.1 to show the reflection of the wave fronts at the barrier. So we have to show the process of reflection of the water waves in terms of the wave fronts. Now this question is mainly done by two different ways, and both the methods are acceptable, are equally effective. So one of them is, I'll be demonstrating only one of them. One of the method is that first of all you select these point of incidence. Point of incidence are the points where the wave fronts are striking the barrier. We choose a point of incidence and we draw a normal line at the point of incidence. So normal line is a line that would be perpendicular to the barrier. And if the barrier is placed like this, a line perpendicular to that would be someplace over here in this direction. So we draw the normal lines first. The very next step is, on the other side of these normal lines, you have to draw the reflected wavefronts and ensure that the angle of reflection equals the angle of incidence. So this is your angle of incidence because this is the angle between the incident wavefront or the incident wave and the normal. So when the wave bends in the other direction, we have to ensure that these two angles remain pretty much the same. First of all, these reflected wavefronts, these ones are representing the reflected wavefronts. First of all, these reflected wavefronts should be on the opposite side of the incident wavefronts. Second, the angle of incidence should be pretty much the same. In principle, it should be exactly the same, but angle of incidence should be equal to the angle of reflection. Third point that you need to consider is, if I consider this one wavefront, right, this one wavefront, then the length of this wavefront was already big before it was going to strike the barrier, and the remaining portion of this wavefront, only that much portion is not hitting the barrier, and the remaining portion would appear as the reflected wave. Similarly, for this one wavefront, its length was not too big compared to the previous one. So for this one, the remaining portion would appear in the form of reflected wavefront. Okay, moving on to the next one, here we have part B. Figure 4.2 shows the wavefronts approaching shallow water above a piece of glass. And the wavefronts are shown over here. Then you have a piece of glass beneath the water. You need to show the wavefronts of the refracted waves. I believe that would be the question. Yeah, complete figure 4.2 to show the wavefronts in the shallow water. All right. So once the water changes the depth, the process of refraction occurs, not the process of reflection. Rather, the process of refraction would occur as the depth of the water changes. And as these waves enter the shallow water, so what's going to happen is the speed of the wave would be reduced, and the wavelength of the waves would also be reduced in the shallow water. And generally, in the process of refraction, the waves bend as well. So the waves should bend on one side as well. But the thing is, in this specific case, the waves are not going to bend anywhere. This is a special case for refraction according to O-level physics syllabus. You need to be careful with one case of refraction where apparently there would be no bending of the water waves. So that case is when the barrier is placed perpendicular to the direction of propagation of waves. Now think about it. Our barrier is placed over here like this. If I just overlap the barrier with this one, this is your barrier, and that barrier is being approached by the waves on the right side. So here we have an angle of 90 degrees. Whenever you have such a case, then there would be no bending of the waves. Now, you just need to represent the wavefronts of the refracted waves with decreased wavelength. And for the decreased wavelength, we have the easiest way. Now for decreased wavelength, it means the separation between any two consecutive wavefronts would be decreased. So all I can do is copy and paste this one with reduced spacing. So once again, spacing between them should be reduced like this, and you draw at least 4 to 5 similar wavefronts with uniform spacing and with decreased spacing. Uniform spacing means the spacing between any two consecutive wavefronts should be equal, and it should be less than the spacing on the incident waves. So this one over here, the wavelength was higher, but as the water waves enter the shallow water, the wavelength decreases. So there has to be less spacing over here in order to show the decrease in the wavelength. And you can draw at least 2-3 more wavefronts, and that would be okay. Moving on to the next one. As the waves passes into the shallow water state, what if anything happens to, first of all, the wave speed? As the waves enter the shallow water, the wavelength decreases primarily because the speed of the water waves also decrease. The wave kind of starts lagging and they bend towards the normal. Their speed decreases, their wavelength decreases. Frequency of the water wave, however, depends on the source that is producing the water waves. If there is an oscillator, if there is a motor, then the speed of the motor would determine the frequency of the wave. So frequency of the wave does not depend on the depth of the water, it stays the same. Frequency stays the same. All right, here we have the next one. Moving on to the next one. Figure 4.1 shows circular wavefront produced at the center of a circular ripple tank. Two corks A and B float on the water in the ripple tank. They move up and down on the surface of the water as the wave passes. The wavelength of the wave is 8.0 centimeter. Figure 4.2 shows how the displacement of A varies with time. So we have displacement time graph. And displacement time graph can be useful to determine frequency and time period of the wave directly. And according to the O-level physics syllabus, we have another kind of graph for general wave properties, that is displacement distance graph. And if it were distance here, displacement distance graph is a graph that can be used to directly determine the wavelength. Anyway, moving on to the first part. State the amplitude of the vibration of A as the wave passes. All right, so the displacement of A is shown in the graph. So the amplitude is maximum displacement from mean position. Maximum displacement from mean position. This is how we define amplitude. So the amplitude in that case would be 2 followed by the units that we note from here. And in that case, the unit is millimeters. If you want to convert it into meters, you can. Otherwise, you can just write it down as it is. The horizontal distance between A and B is half the wavelength of the wave. Right? So the distance between this one and this one is half the wavelength. So it would be something like this. If I try to draw the wave, yeah. Now you see the distance between A and B is half the wavelength from here to here, because that is the distance between two consecutive crust and trough, half the wavelength. And wavelength, by the way, is distance between any two consecutive in phase point, any two consecutive crust, which is 8 centimeters. Given in the question as well, given in the diagram as well, given in the description as well, that the wavelength lambda equals to 8 centimeter. So the distance between A and B would obviously be then half of 8 centimeter, which is 4 centimeter. So A and B are 4 centimeter apart, these two corks. On figure 4.2, sketch a graph to show how the displacement of B varies with time. So since these are half the wavelength apart, so whatever, if there is crust on the cork A, then cork B would be having crust, a trough. Because half the wavelength means it would be exactly opposite thing going on for the other one. So for the first one, you see there was, this is the graph for the cork A. And for the cork B, which is half the wavelength apart, it would be exactly the opposite thing going on. So first I can draw some of the reference points to which I'll be passing my wave from. So that'll be something like this. All right, and the red one is representing the wavelength, the displacement time graph for the cork B. And why is it exactly the opposite? Because the distance was half of the wavelength. If the distance were full wavelength, the distance between A and B were full wavelength, or a multiple of integer multiple of full wavelength, I mean lambda, or 2 times of lambda, or 3 times of lambda, we call it integral multiple in mathematics, or 4 times of lambda. In that case, the graph for the cork B would have been exactly the same as for the cork A. So there would have been an overlap. But since these are half the wavelength apart, so exactly opposite stuff would be going on for the cork B. Anyway, moving on to the part C. Use figure 4.2 to determine the frequency of the wave. So we need to find the frequency of the wave. That is kind of an easy one. Once you're provided with the displacement time graph, you can easily find frequency. Now, it can be obtained by different ways. One of them is you can find the time period first and then find the frequency. Or the other method is you can directly find the frequency if you somehow know the number of waves in 1 second. So the 1 second mark is here. All I gotta find is how many full waves cycles are there till 1 second. So if I start noticing it, this is the first wave ending over here, and there after that I have another wave ending at 1 second. So in 1 complete second, there are 2 full wave cycles. So the frequency of the wave would be 2 hertz. Frequency of the water waves, uh, matter of fact, frequency of all the waves in our O-level physics program we represent in hertz. Then we have the next one, the distance between the center of the ripple tank and its edge is 40 centimeter. Determine the time taken by the wavefront to travel from the center of the tank to the edge. So this is the next one that we need to calculate. All right. So for this one, we know that the distance is given 40 centimeter. You can represent distance by s as well. Determine the time. We need to find time for the wave, and the formula that relates distance and time is mainly this one: speed equals to distance over time. And from there I can make time the subject because I need to find the value of time. So time would be distance over speed, and the speed of waves is represented by another formula, that is frequency times wavelength. So the distance divided by frequency times wavelength. Now the distance is 40 centimeters and the wavelength was 8 centimeters. So I'm not doing any conversion because both the units of length are in centimeters, so they'll be cancelled out automatically. So yeah, that was the value of wavelength, and the frequency was 2 hertz, I think. Yeah, 2 hertz. After that, you can just hit it on the calculator. No need to waste any time over here. 20 here, and final answer would be 2.5 seconds. All right, we just hit it on the calculator from here, and we get to our final answer, which in this case would be 2.5. Moving on to the next one, here we have title as question 6. Figure 6.1 shows a wave on the surface of the water. The wave is traveling to the right. All right, I can draw the direction of motion of the wave, which is on this side, to the right. Then, describe what is meant by the wave motion for 2 marks. Now the thing is, to be very honest, I tell you every time to my students that we are preparing for O-level physics program, and when you're approaching the theoretical questions, you need to ensure that you write the terms which are recommended, which are encouraged by the examiner, which are written in the marking scheme. How do you know that? You read through the learning objectives, especially the definitions and everything. They specify in the learning objectives that you should be defining these terms. So always, because we are preparing for a certain exam, right? It's okay, sometimes your concept might be right. In terms of principles of physics, your concept or your definition or your answer might be right, but if you're not explaining in terms that are appreciated, that are encouraged, or that are demanded by Cambridge, you may not be getting full marks in that. So how do we define this one for the wave motion? So wave motion, we define it a periodic motion in which energy is transferred from one point to another from one point to another without net movement of particles. So the particles, they keep vibrating on their position, but they do not move from one place to another without net movement of particles. So this is how we define the wave motion, and these are in the terms that are appreciated or encouraged and probably demanded by Cambridge. So make sure you're writing the keywords. So the keywords in this one, first of all, a periodic motion, energy is transferred, this one, from one point to another, and with, sorry, I missed the most important thing here, with no net movement of particles. This was the most important thing. With no net movement of particles. And also the other important thing was no net movement of particles. So these are the key terms. Always write your answer in these key terms. On figure 6.1, draw an arrow to show the direction of movement of water molecule at x. So this one we have, like I explained this one in my previous lesson as well. In order to explain the motion of this particle, first of all, you have to be sure that this particle is either going to move up or down. How do we know that? Because if the wave is traveling on the right side and this is a transverse wave, so it can only move up and down, because in transfer waves the particle vibrate perpendicular to the direction of wave transfer. So if wave is on the right side, the only way we can be perpendicular to this right side is by moving up and down. Now, how do we know which direction do we choose from? Now, the particle X has already received the maximum amplitude, and as the wave moves to the right side, so probably this portion, I can just make a box over it, this portion, this displacement of the wave would now be transferred to the point X. Point X was previously be having, let's say, displacement 5 centimeter. Now this displacement that is behind that point is not 5 centimeter, is slightly less than 5 centimeter. So once this displacement is provided to the particle X, it would move downward, because now it'll be provided with less displacement. And the easier way to memorize this one is, if you fail to understand this one concept, then what you can do is, if all the points that are in the upward slope and the line rising up, those particles would move downward if the wave is moving to the right side. And matter of fact, also if the wave were moving on the left side, because either way they'll be now provided with less amplitude, less displacement. So wave move, this particle moves downward, because it was in upward rising portion, it was sliding up, it would move downward. And if it's the other way around, if the particle was, let's say, someplace over here and the wave is moving to the right, now this particle would then move upward, because it'll be getting higher displacement from what it is already having. So this is just for an assumption. If there were a particle y, that particle y would have been moving upward like this. That is not part of the question. The frequency of the water wave is 2 Hz and the wavelength is 2.5. Calculate the speed of the wave. Now this is kind of an easy one. So all you have to do is apply the formula for speed of waves. So speed v equals to frequency times wavelength. And frequency is given as 2 Hz. 2 times 2.5, and that would be 5.0. centimeter per second. This is per second. Hertz is also called per second, and we get centimeter from here. If you wanted to convert centimeter into meters, you can, and then you can write meter per second with your answer. Otherwise, if you don't want any conversion, then your answer has to be consistent with whatever units you have chosen. Move on to the next one. On figure 6.1, mark the distance which shows how far a wavefront at x moves in 1 second. Label this distance d. So in 1 second, how far the particle moves. So the frequency of the water wave is 2 hertz. It means in 1 second, 2 waves would be completed. In 1 second. In 1 second, 2 waves would be completed. So that 1 second would mean the particle x would move 2 waves, 2 cycles forward. So your particle x, this one would be the first cycle, and it would move 2 cycles forward. So your particle x would now be at this position over here. And what do we need to mark it with? Let me just check it out. Label this distance d. Okay, so we have to label the distance. So this one would be yeah, we can draw a line to represent the distance, and make sure that the line is exactly from the first point to the other one, not in the middle, not extending beyond the points, just exactly from end of the first point, from point to point. So this distance has to be labeled as distance d. So we can call it distance d. Alright, then we have the next one. A water waves of frequency 3.6 hertz is generated in a ripple tank. Figure 5.1 is a scale diagram. Scale diagram means it is drawn to a certain scale, showing the wavefront of the okay, so length of 1 centimeter on the diagram represents 8 centimeter on the ripple tank. So if you measure 1 centimeter from here, actually it would be 8 centimeter on the ripple tank. Anyway, using measurements from figure 5.1, determine the wavelength of the wave in the deep water. Alright, so that's an easy one. So all you have to do is take out your ruler and measure the distance from this point, from the first wavelength to this next consecutive wavelength. That would be your wavelength on the sheet of paper. So let's say I can't do it with the help of a ruler. So I assume that this distance is, let's say, 3 centimeter, or let's just call it 2 centimeter. So, all right, so this is a supposed value. You do it with a ruler, measure the distance between two consecutive lines, whatever it is, you just write it down. Since I can zoom it in, distance would be increased. If I zoom it out like this, distance would be decreased. So I'm not going to write any certain value. So I assume that on the sheet of paper, the distance is 2 centimeters. So this 2 centimeter is the wavelength on the sheet of paper. According to the scale, 1 centimeter on the sheet of paper represents 8 centimeter in the ripple tank. So 2 centimeter on the sheet of paper would represent 2 times of 8 centimeter on the ripple tank. So 16 centimeter. Once again, this is an assumed value. I don't know the exact value. Exact value there would be, it would be depending on the actual value that is measured with the help of a ruler. Calculate the speed of the wave in the deep water. In order to measure the speed, you just multiply frequency by the wavelength. This is your frequency 3.6 hertz. So then you start it out. Speed of the wave is frequency times wavelength, and frequency was 3.5 times 16, and then we just take out the calculator. 16 times 3.56, and the unit in that case would be centimeter per second. Where do we get the centimeter from? Because 16 the wavelength 16 was in centimeters and the frequency was in hertz or per second. So centimeter, this is how we get centimeter per second.